Okay, this is going to be your second lecture for Chapter 5. This is Chapter 5.4 through 5.8. And so we're going to be talking about the real gas law. We're also going to introduce something called Dalton's law of partial pressure. And we'll also talk a little bit about molar volume and molar masses. So I'm going to start with a review from last time. Last time we talked about the combined gas law. And so in this scenario, we have the volume of oxygen gas in the balloon at 1 atmosphere and 305 Kelvin, with a volume of 0.65 liters. Now from there, we want to calculate the volume of the gas after the temperature is allowed to lower to 77 Kelvin while keeping the pressure and the amount of O2 constant. So we have a before situation here, and we have an after situation there. And so we want to try to come up with our answer. So I'm going to give you a moment, pause the video, so that way you can go through and try to find out what you think it should be for this volume. Now, when I get a problem that looks like this, what I want to do is start by first breaking out my information that's inside. And so I have a couple of different things that I want to start writing down. One is that I know that the volume of my oxygen gas is 0.65 liters. That's going to become my initial condition. My temperature in my initial one is 305 Kelvin, and my pressure at my initial one is 1.0 atmosphere. Now, I don't know my initial number of moles. That's kind of up in the air. But when I look at my second equation, I know that my volume is what we're looking for. My temperature is going to be at 77 Kelvin, and my pressure is going to be 1.0 atmospheres because it's the same. My moles is going to be equal to my initial, so that's the same as well. So there's two things that I could do. One is I could take my initial conditions, turn that into a normal ideal gas equation because we have volume, temperature, and pressure. I can use that to find my N, and then I can take that N and plug that into my second equation and use that to find my volume. But that would take me solving the equation twice. Instead, I can just set them equal to each other. P1 V1 over R, or not R1, N1 T1 is equal to my final pressure, my final volume, my moles final, and my temperature final. I can then remove what has stayed the same, so my pressures have stayed the same. My moles have stayed the same. And so now I have a relationship between my volume and my temperature, and we're looking for this volume here. So I can rewrite my equation as the final volume is going to be equal to my initial volume divided by my initial temperature times my final temperature. So that becomes 0.65 liters, 77 Kelvin, 305 Kelvin. Now, one thing that I'll tell you is that in this case, everything's in Kelvin, and so we don't have to worry about it. But when we start to do these, if your temperature is not in Kelvin, you have to make sure that you convert it into Kelvin. And the reason for that is that if you leave it in degrees Celsius or Fahrenheit, they're not going to give you the correct ratio that we need. So 0.65 times 77 divided by 305 gives us the answer of 0.164 liters, which is going to give us our answer of 0.16 liters. And that's what we're looking for. Okay. And so that's us applying that combined gas law in motion. Let's look at another one. Or not look at another one. Let's move on. So in our next one, what we're going to be talking about is Dalton's law of partial pressure. Now, Dalton's law of partial pressure is kind of this idea that in an ideal gas mixture, so if we're treating all of these gases as being ideal, what we'll notice is that their total pressure is going to be equal to the sum of their parts. So that's the pressure that's related to one of those gases. So like above, it could be our oxygen. This would be our nitrogen. This would be our argon, and so on, all making up the pressure that would be our air. So it's equal to the sum of all of those parts. So looking at our example down here, if we have a partial pressure of our oxygen at 159 millimeters of mercury and nitrogen is being 593 millimeters of mercury, then our system together should have a total of 159 plus 593, giving us 752 millimeters of mercury. So Dalton's law is assuming that all of that part stays the same, right? That their total pressure is equal to the sum of each of its parts. And because we have the ideal gas law, that means that if the pressures are equal to the sum of their parts, then so is the volume and so is the moles, and technically the temperature as well. Now, we normally don't see it for a lot of these other ones, but we do see it often for pressure, and we do see it for N a lot. So let's try that out. We have a mixture of 4 moles of hydrogen gas, 8 moles of oxygen, 12 moles of helium, and 6 moles of nitrogen in the closed container. What is the total number of moles in this system? So we need to start by applying that partial pressure law. And so we can add the moles up, and our system would have 30 moles of gas inside there total. Now, moles are sometimes a little bit easier to imagine because you can imagine that you have a box, and when you put in 1 mole of that hydrogen, that's going to stay in there. And if you add in nitrogen, that is also going to stay in there. And so we can see how when we ask the number of moles that are inside, how that part has stayed the same. That part has stayed constant. But if you want to think about it, each of those moles kind of gives a certain amount of pressure. And so that's why the pressure also stays constant. So a total pressure will be equal to all of their parts on the inside. So let's answer this question. What is the partial pressure of oxygen in a mixture that contains 0.3 moles of O2, 0.7 moles of N2, 0.25 moles of AR, and it has a total pressure of 1.1 atmospheres? So we know that our total is 1.1 atmospheres. Now, from there, we know that 0.30 moles of O2 plus 0.70 moles of N2 and 0.25 moles of AR is all of that material inside. So if we add them all up, we find out that 1.25 moles gives us that total pressure. Now, if 1.25 moles gives us that 1.1 atmospheres, then we also know that our partial pressure of oxygen would be 0.30 moles of our oxygen divided by 1.25 moles. That's a fraction that must be coming from our oxygen. And so if we multiply that by 1.1 ATM, that's going to tell us our pressure that's coming just from the oxygen in ATM. So what I did there was I used our mole fraction. I set up how much oxygen we had, so the moles of our oxygen, divided by our total moles. And that gave me that fraction, how much of that total pressure was coming from our oxygen to get our partial pressure. And so those things can be kind of moved in between each other as you're going through that. Now, last time we mentioned very briefly STP. And so we should be able to write that down. What is STP? It does stand for something. It stands for standard temperature and pressure. Now, this is the standard for these sets of experiments. That doesn't mean that at different experiments, we might have a different set of standards, but whenever we're dealing with ideal gases, STP is going to stand for a temperature of 0 degrees Celsius or 273 Kelvin and a pressure of 1 atmosphere. Now, when we get into thermal chemistry, sometimes that value is going to change when you talk about standards. And so you really want to make sure that you're paying attention to which kind of standard they're talking about. And so for gases right now, this is our STP. And remember that 1 atmosphere is also equal to 760 millimeters of mercury. So let's look at another one. Which of the following will have the greatest volume at STP? 5 grams of H2, 5 grams of N2, 5 grams of O2, or 5 grams of carbon monoxide? All of the above have the same volume. So what do you think? How does that work? Now, when we're looking at this, remember that our equation for gases, PV equals nRT, is our ideal gas equation. When it's talking about the amount of material there, that's showing up as our N term, and that's our moles. Now, over on our left, that's our mass. And so while that's talking about the amount of material, it's not talking about the moles of material. And so we need to first convert all of those into our moles. So we need to change our H2 into our moles of H2. And we can do that by dividing by its molar mass, which is 1.00794 times 2. And so 5 grams divided by that, this gives us 2.48 moles of H2. N2, its molar mass is 2 times 14.00679, 74. And so it's 5 grams. It's a lot less, 0.1785 moles. O2 gives us 0.1563 moles. And carbon monoxide gives us 0.1785 moles. So if it's asking us which of these will have a greater volume, we want to think, well, the more moles we have, is that going to increase our volume or decrease our volume? And so if our N term is increasing, so that means that this N term over here is going up, then that's going to impact our P and our V. Our pressure is staying constant, so our volume must also go up. And so we want the highest volume, and so we want the most number of moles. And so that's why we should be selecting A. Now, we did talk about that at STP, 1 mole of gas always has the same volume, 22.4 liters, no matter what it is. And that's because we're assuming that it all behaves ideally. And so you can get this by solving for 1 mole at STP, so that's 0 Kelvin, or not 0 Kelvin, 0 degrees Celsius and 1 atmosphere, and we get that 22.4 liters. This is called the molar volume. And so while 1 mole measures of different gases have different masses, they all have the same volume. So their densities will be different, but their volumes are all going to be the same because the number of moles, if it's 1 mole of gas, it gives you the same volume, but their mass will be different because this is impacted by their molar masses. And then in that regard, it doesn't matter what the mole is, as long as it's a mole of an ideal gas. So the 4 most common gases in the atmosphere are N2, O2, AR, and carbon dioxide. Assuming all gases are in containers of equal size, temperature, and pressure, which gas has the highest density? So think about that. Now, if we're looking at this, they are all in an equal size. So that means their volume is the same. Their temperature is the same. Their pressure is the same. So the only thing that can change is our N. Now, if their volume is the same, the pressure is the same, their temperature is the same, then their moles is also going to be the same because they are all solving the same equation, PV equals nRT. And so if all of those other 4 variables are the same, then those N's have to be the same. But density is not just N. Density is a mass divided by our volume. So while N is the same, their mass is not the same. Their mass depends on their molar mass. So if we take their molar mass times N, that's how we get their mass. So if they have the same number of N's, then whoever's going to have the highest molar mass is going to have our highest density. So this question is asking you which one has the highest molar mass, essentially. because that's going to give us our highest density. So if we look at that, nitrogen is something about 28, O2 is about 32, AR is 40, but carbon dioxide, now that's 36 plus 12, so that's 48. And so carbon dioxide is going to be our winner there. Carbon dioxide is going to have its highest density. Let's try another one. 3.50 grams sample of a diatomic gas in 1.5 liter container has a pressure of 2.42 atmosphere at 355 Kelvin. What gas is it? Now, there are two ways that you can do this. And so I want you to go ahead and try a way. How do you think you could solve this? Now, when it's asking us to determine the identity of a gas, what we're thinking about is molar mass. And molar mass is the mass divided by our moles. Now, we already know our mass. We know the mass is 3.50 grams, but I don't know the moles of it. So I'm looking for N. And so I can solve PV equals nRT. PV over RT is equal to N. And so what I need to look for is my pressure, which is 2.42 atmospheres. My volume, 1.5 liters. My temperature, 355 Kelvin. And then my R, 0.08206 liters atmospheres K mole. Once I have that, I can go ahead and plug those in. And we find out that we had 0.1246 moles of N. So 3.5 divided by our moles gives me a molar mass of 28.09 grams per mole. And so all I did was I replaced this 3.5 and I divided by my N value that we had found. Now, if I have a molar mass of 28.09, I can compare my molar masses with these other ones, and we can find it to be B. Now, another way is that you can turn the ideal gas law, PV equals nRT, to be looking at molar mass. By using our molar mass is equal to mass divided by N, what we can do is we can take our molar mass, we can take our N is equal to PV over RT. And so we get molar mass is equal to M over PV over RT. And if we condense that down, we get M over, so MRT over PV is equal to our molar mass. So that's the second way that you could find that as well. Right? So either one works. I find that doing it all at once requires me to keep track of another formula that I have to memorize, which seems like too much work. So I prefer to do it in my two-step process. Right? But either one will work. Let's look at another one. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury do we need to synthesize 35.7 grams of methanol? So that's a lot going on. And so we have two things. We have a reaction up here where we're trying to make methanol. So that's this product here. So for us to do that, we first need to take and figure out, well, if we have 35.7 grams of methanol, how much hydrogen do we need for that? So we need to convert that methanol into moles. So we know that methanol has a molar mass of 12.0107 plus 4 times 1.00794 plus oxygen. We know that methanol has a molar mass of 32.04186 grams per mole. So this 35.7 grams of methanol, I can turn that into 1 mole of methanol is 32.04186 grams. Now, we're looking at our volume of hydrogen gas, and so we want to change that into hydrogen gas. And so 1 mole of methanol requires 2 moles of hydrogen gas, which I'm guessing from this balanced equation up there with its coefficients. And so if we do this conversion, then it's going to tell us how many moles of hydrogen do we need to make that reaction occur. So we need 2.228 moles of hydrogen. So now what I want to look at is, well, what volume do I need in order to produce 2.228 moles of hydrogen? So PV equals nRT. My volume is nRT over P. My R is 0.08206 liters atmosphere, K mole. My temperature is 355 Kelvin. And then my pressure is 738 millimeters of mercury. Now I can't use that yet because I have to first convert that into my ATM. So 738 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. That gives me 738 divided by 760, 0.971 ATM. Now I can take that and plug that in. 2.228 times 0.08206 times 355 divided by 0.971. And we find out that we need a volume of 66.84 liters. Well, in this case, we're really looking for 66.8 when we think about significant figures for our volume. So now that we have our ideal gas, we can fit that in as another part of our equation. We can use all of those same things that we've done before. I'm just trying to get the whole right up. There we go. And we can plug those same things that we've known into our equation. And so now we can find that volume as well. So in the same way that we've been dealing with all of these stoichiometry problems, we've now added another container to it. Instead of only being able to go from our grams to our moles for a solid using the molar mass, we can also go from the volume of a gas to our moles using the ideal gas law. Could also be pressures, could also even be from a temperature, right? So we know a lot of information. So there's different ways for us to convert from one to the other. And so there's some more practice ones that you can do. Like this one is a good one to practice. The next thing that we're going to look at is collecting gases. Now, gases are often collected by having them displace water from a container. So you might have a container flipped over inside of a big tub of water. And so we would fill that container with water. Now, as our gas comes up inside, it starts to erase or push down that water. And then we can measure that volume of that water displaced. Now, the problem with that is that inside this container, it doesn't just capture a gas. It also captures some amount of water. And that's because the water can turn into water vapor. So all the time around us, some of that water isn't just staying as a liquid. Some of its really fast particles break free from the surface and turn into a gas phase, the water vapor. Now, this is something that increases as the average temperature increases and decreases when your temperature goes down. So that's why when it's hot out, we normally see more humidity. And when it's cold out, then we see less humidity. But that also depends on how much water is in the air, right? It could be really hot in the desert, but if there's no water there, then your humidity is going to be low no matter what. Now from here, this means that if we're capturing water, we always have to account for the vapor pressure of that water if we capture a gas above it. Now, the nice part about that is that because this is so commonly done, it's often given as a table. And so we can find the partial pressure of water vapor in the gas we collect because it's going to be given to us as a container. So if we collect a gas sample with a total pressure of 758.2 millimeters of mercury at 25 degrees, 23.78 grams of, or 23.78 millimeters of mercury of that is the partial pressure of the water vapor. And so our dry gas that we captured is really only this pressure here. And so that's what's going on with here, is that you're getting a whole temperature range that has the partial pressure for water for each one of them. And so you can kind of see in this scenario, this is similar to what we've done where we dissolve the zinc inside of the HCl and you made the bubbles. Well, in this time, instead of capturing it with a just empty test tube, we bubbled that over through some water and we're capturing it inside this container here. Now that container, because it's above water, isn't just that gas. Instead, it has some of that water vapor in. And so that total pressure is the pressure of the gas we want plus the pressure of the water that's turned into water vapor. And so depending on your temperature, then we can find the partial pressure of that water going all the way up. Now, the hotter it gets, the closer to boiling it gets, then the higher and higher that partial pressure will go. Now, there's going to be a worksheet that's attached to this lecture page that's having you deal with this. This is something that you're going to want to do. Our lecture is going to be shorter today because I want you to practice doing this type of collection. And so there's going to be a video that's connected with this, as well as this worksheet. You're going to want to work through that video and the worksheet so you can determine this. Right? And so you're going to practice collecting a gas above a water displacement so you can figure out what that looks like. Now, the general idea is that we can use the PV equals nRT to get to our moles of our gas. Once we have the moles of our gas, we can use our chemical equation to get to moles of something else, and then we could turn that back into either grams, or we can also even turn it to other things for another gas. Right? So ideal gas law becomes important because we can use it in our toolbox to do more of those stoichiometry changes as we move back and forth through our chemical reactions. The second thing that we've talked about is we've talked about ideal gases as being ideal. But one of the things that I always want to stress is that we should also know when gases are not ideal. So we know when we shouldn't use the ideal gas law. When is it going to be a problem? Now, the image here is not quite as good as it is in the slide pack, so I will encourage you guys to look at the slides if you're struggling to see this diagram here at the bottom. Right? For whatever reason, it's not coming through in its color as well. But real gases often don't behave like ideal gases, and this is going to be at high pressure or low temperatures. And the reason why is at high pressures or low temperatures, we made two big assumptions before for the ideal gas law, was that the attractions between the gas molecules didn't exist, and the gas molecules do not take up any space. And so this kind of came from that kinetic molecular theory. Well, at low temperature and high pressure, then those are no longer valid. Now you can see that generally speaking, they always kind of stay within that range. Our ideal gas, it would be 22.41 liters. N2, helium, they all kind of close to that, but things like chlorine and carbon dioxide, they start to drift more away from that. And so the reason why these things have an impact is that it depends on the different scenarios. So at low pressure, the molar volume of argon is nearly identical to that of an ideal gas. But as the pressure increases, the molar volume of the argon becomes greater because as we go to higher pressures, the argon atoms themselves begin to take up some of that space. So you can imagine that if you had a container, that container might be big. Maybe it's 1,000 liters. But as we start to put gas in, if it's a low pressure, then there's only one of those atoms inside that whole space. So let's say that that one atom only takes up a very small portion of it. And so the space that it occupies is not much compared to the overall grand scheme of things. So maybe instead of 1,000, we're at like 999. Not too bad. But as we keep going up, then it becomes more and more of a problem. So as we keep going up, as we keep increasing our amount of our argon, so our gas particles inside, as it goes up, we're increasing the amount of our gas particles inside. And so now, if we have 100 of these, we can no longer ignore them. So instead of being 999, which is really close to 100, we're at 900. So that space that it occupies, it actually really starts to impact the total volume, because those particles can't be exactly where the other particles are. They take up some of that space. So as our pressures get higher, we get more and more of this as an impact, because the fraction of volume that's occupied by those particles matters more and more. So for a real gas, because they take up space, then their pressures, at higher pressures, the volumes are generally higher than predicted by the ideal gas law. So you can start to see that green line coming up above. But you can see that this really only started after 200 atmospheres or so, where we start to see where those lines can differentiate from each other. And so that's why it only really matters at a really high pressure. Anything below that, we kind of have a hard time telling. And so van der Waals, in 1873, he decided to modify the ideal gas behavior in order to account for those real gases. And so what he did is he added in this constant B called the van der Waals constant. And it's different for each gas because the molecules are different sizes, but it's this idea that there's some amount that we have to adjust that volume for to account for how many moles of gas there is based on that pressure. Now, you don't have to memorize these new equations for the real gases, but you should know why they are impacted and how they are impacting things. That conceptual part is the part that we're trying to address. On the other side, the high temperature and the low temperature, this has to deal with their attractions between each other. So at high temperature, the pressure of the gases is nearly identical to that of an ideal gas. But when we get to lower temperatures, the pressure of the gases becomes less than that of an ideal gas. And this is because at lower temperatures, the gas atoms spend more time interacting with each other. That means that they're interacting with each other, so they're colliding with each other, or they're spending time with each other more than they're colliding with the walls. And so this makes the actual pressure less than what we would have predicted. So as we're lowering or slowing down that temperature, it's almost like these particles, instead of running around at full speed, when they're going slower, they can reach out and they can hold on to each other. And because they can hold on to each other, then they don't collide with as many things. It would be kind of like if you went to the roller skating ring with your friends. If you guys are roller skating around very quickly, then you're never going to really catch each other from the side, right? You're not going to be able to reach out and hold on to your other friend because they're going to fly on by. But if we slow them down, if everyone's skating nice and slow, someone on the outside could reach on out and you could grab their hand, and now you guys would now be moving in slower. And so what's going on is that these gas particles, instead of zooming on by each other, there's an attraction between them. They get to spend more time with each other. And if they're spending more time with each other, they're colliding less with the walls. And so that's bringing our pressure down. And so van der Waals had another modification for this. And so he modified the ideal gas equation with an A factor. And that A factor deals with the fact that each gas has different attractions because of what makes them up. And so when we go to lower temperatures, then we start to see that have an impact. So overall, our real gas equation looks a little bit more complicated than our ideal one. So instead of PV equals nRT, we get P, which is addressed by this correction for the attractiveness, and it's V, which is addressed by this correction for the particle volume. is equal to nRT. Now, that means that for a real gas, you would have to use these different values there to adjust for them. And you can see that some of these molecules have really intense attractions. Something like carbon tetrachloride, it's got this attraction of 20, whereas our ideal gases might have a very low attraction there. Our bigger molecules also have a bigger correction for their volume, whereas our smaller ones, like helium, have a much smaller correction. And so you can kind of plot these out, and what this is showing you is that the P equals RT ratio for a real gas is generally going to be lower than that of an ideal. And that's because, if it's lower than that, than the ideal, then that's because it has an important factor in the intermolecular forces. If it's higher than the general curve, then that means that a more important factor is going to be the molecular volume. And so this is our ideal gas curve right here, the straight line. And you can see down here, this water is being driven by its attractiveness. So there's attractive forces. Whereas things like xenon or neon, those are being driven by their size. So for these, I'm not as concerned with you applying all of these to mathematically solve real gas problems, but I want you to understand where the ideal gas law starts to break down. And that's because sometimes when we start to use these laws over and over again, we assume that they're true in all cases and all scenarios, and that part's not. And so I don't want you to run into a problem later on where you're applying it when you shouldn't, right? And so an example of this is in graduate school one time, I was given the task of trying to figure out how many moles of gas there were inside of a high pressure tank, that carbon dioxide. And so I looked at the volume of the tank, I looked at the pressure, and I did that simple math, and that was the estimate that I came up with. And it was only later on that I realized that that was actually a very poor estimate, because that carbon dioxide that was in there at 500 ATMs was really not behaving ideally. And so when I went back and I used the corrective fraction, like what's on here, it made a huge difference in how much was going to be inside of that volume. And so it's important to always know when does that ideal gas situation break down and when should be looking at a real one. So we're going to do a little practice problems, right? So for this one, go ahead and try to calculate your answer, and then we'll go through that answer. So 267 grams of solid silver chloride is heated until it decomposes to form a diatomic gas and a mellow solid. So we got to figure that part out. If the entire solid decomposes, what is its volume collected above pure water? Assume that the pressure of the total gas collected is 1.00 atmospheres and the temperature of the water is 30.00 degrees Celsius. Okay, good luck. Okay, so let's go ahead and get this started now that you've had a chance to try it out. So let's start with our chemical reaction. Now we know that silver chloride is what we're beginning with, and we're going to heat that, and it's going to break down into some diatomic gas and a solid. Now really the only mellow solid that we can form from silver and chlorine is going to be silver. And if that's what's breaking down, then we must be left over with our gas, which is our chlorine, and it's diatomic, so that's Cl2. We should balance this, so we would get 2 of these and we would get 2 of those. Okay, so 267 grams of our solid silver chloride is breaking down into 2 silvers and then 1 chlorine gas molecule. All right. Now we're thinking the entire solid decomposes. And so all of that is happening. We're then going to capture that in the container above water. And inside that container, where we don't know what volume it is, that's what we're looking for. But we do know that the pressure is 1.00 atmospheres, and that's the total pressure. We do know that the temperature is 30.00 degrees Celsius. And our N, we don't know yet, but we should be able to figure that out. So let's start with that. If we have 267.00 grams of AgCl, we should be able to figure out how many moles of chlorine that should be. if all of it decomposes. So silver chloride is 107.8682 plus 35.4527 grams per mole. So that's 143.3209 grams per mole. So this 267.00 grams of silver chloride can become 1 mole of silver chloride at 143.3209 grams of silver chloride. And we know 1 mole of Cl2 is 2 moles of silver chloride. And so we can find our N this way, 267.00 divided by 143.3209 divided by 2. And so we have an N value of 0.931476. And so we can use that for our N. Now, I'm going to change my temperature because it's 30.00 degrees Celsius. So I need to add 273.15 to that to get into my Kelvin. So that's 303.15 Kelvin. Sorry, I've been writing this all the time, and now I realize that it didn't capture. So what I did was I set up our equation here. After that, I wrote down our volumes here. I then also set up our molar mass to find our moles here. Now I'm going to update my temperature. This temperature is now going to be 303.15 Kelvin. And then we know that our pressure total should be made up of 2 things. It should be the pressure of our chlorine gas, but it should also be the pressure of our water because we're capturing it above pure water. So what that means is if we go back to our equation sheet here, at 30 degrees Celsius, our partial pressure should be 31.86 millimeters of mercury. So if we go back to our total pressure here, we know that 31.86 of those millimeters of mercury should be our pressure of our water. And if I want to turn that in ATMs, I just divide that by 760. And that gives me 0.0419 ATM. And so if I take 1.00 atmospheres minus 0.0419 ATMs, that's going to give me my pressure of my chlorine. Which is going to be 0.958. So my pressure of my chlorine, I can now update that. And now we can find our volume. So I can look for my volume is going to be our N of our chlorine, our R, our T, over our pressure of our chlorine. Now we don't want to just use our total pressure because then we would have to know our total moles. And that means we would have to know how many moles of water vapor we had to include as well. Instead, we'd rather just use our revised pressure, so the pressure of just the chlorine, because then we can use the moles of just the chlorine. So updating this, that becomes 0.931476. And if we wanted to think about significant figures, we'd have a total of 5. Our R, which is 0.08206 liters atmosphere K mole, of course. Our temperature is 303.15. running out of space here. Let me just move this all over a little bit. We'll just swap the color, make that a little bit easier to see. And so what I'm doing with those lines is those lines I'm using to kind of signify where my significant figures should be, just so that way I don't have to do all that rounding yet, because actually for most of them, I could probably wait and do all of them as one giant problem and then do my significant figures. So I don't want to round too soon, but I do just want to have them marked so that way I know that not all of those values are significant. And so once we've gone through all of that, our volume of our chlorine comes on down to 24.188 liters. And if we think about significant figures, we should only have 2 because our pressure only has 2 significant figures, which brings us to 24 liters. So let's go back to our screen, and we can now look at another one. How many grams of oxygen gas are produced if the sample is captured above water at 20.00 degrees Celsius at 755.2 millimeters of mercury and a volume of 1.02 liters? So in this case, we're looking for our grams of oxygen, and we can find our grams by going through the moles of oxygen. So N is what we're looking for. Our pressure is 755.2 millimeters of mercury, and that will be our total pressure. Our volume is going to be 1.02 liters, and our temperature is going to be 20.00 degrees Celsius. So we want to update those, turn them into Kelvin for our temperature, so that becomes 293.15 Kelvin. Our volume is okay. Our pressure total, we got to subtract the water vapor, so 17.55 millimeters of mercury. And we got that from looking at our 20 degrees Celsius and how much water that should be. So that changes this from being our total pressure to being our pressure of only our oxygen at 737.65 millimeters of mercury. We divide that by 760 to get that into ATM. And now we're going to solve for our moles. So N is equal to PV over RT. So pressure 0.097059 times our volume 1.02 divided by R 0.08206 divided by our temperature 293.15 gives us our N of 0.04115 moles. And so if we want to get to grams, we just need to take our N and we need to multiply it by its molar mass. And so 1 mole of O2 is 15.9994 times 2. So 31.9988 grams of O2. And that becomes 1.317 moles or grams of O2. If we wanted to think about significant figures, our volume only has 3. And so that's probably going to be our significant figure limitation. And so this one, instead of being 1.31, should become 1.32 grams of O2. And so there's some sample problems with that one. Now, the last part of what we want to talk about is a little bit about this temperature and molecular velocities. So temperature is related to the kinetic energy of a particle. And so kinetic energy can be defined as 1/2 of Avogadro's number times the mass of something and the velocity of the particle. So the idea behind it is something that's really big, something that has a lot of mass. The faster it goes, the more kinetic energy is inside of it as a square factor of its speed. Now, if you have a small object going fast and the big object going fast, the bigger one is going to have a higher kinetic energy associated with it. It's kind of like throwing a baseball at 15 miles per hour versus throwing a bowling ball at 15 miles per hour versus throwing a tennis ball at 15. Each of those has a different mass, and so the kinetic energy behind them is going to be different. As you can imagine, getting hit with a tennis ball going at 15 miles per hour is not nearly the same as throwing a bowling ball at 15 miles per hour and getting hit by that. Now, that kinetic energy is related to the amount of energy inside, which can be summarized by this equation here, 3/2 over RT. And so it's related to the gas constant times the temperature. Now, all in all, what this is going to is telling us that there is some relationship between the velocity of our particle. So that's this U, the RMS stands for root mean squared, which has to deal with how you determine that velocity and basically that it moving in like a straight line. But you don't have to worry about that part. But what you do want to know is that it's related to the mass of that particle, as well as these constants. Now, what that tells you is that anything that has the same average kinetic energy, the heavier molecules have a slower average speed. So if we're really looking at the speed, all of these are given the same average kinetic energy, but they're just different masses. So our hydrogen, which has its lowest molar mass, it on average moves faster than all of the other particles because if they have the same temperature, so they have the same average kinetic energy, its mass allows it to move much faster in order to impact that same amount of energy. So hydrogen goes much faster compared to things like helium, and then oxygen, which has its highest molar mass, comes at the end. So really, this is the takeaway that I want you to know, is that at the same temperature, the smaller molecule, in terms of mass, has a higher speed. Now, if we increase that temperature, then things change because their kinetic energies would also change and they would all speed up. But as long as they're at the same temperature, then whichever one has a smaller molar mass is going to have the higher speed. And that's it for today. So now that you've kind of gone through this and you've done some practice problems, the next thing that you want to work on is that worksheet. So there's going to be a video. We're going to basically kind of do a group experiment where we're going to dissolve some magnesium. We're going to capture that gas that gets generated, and we're going to produce, and we're going to work through capturing that gas. So that's what's going to be next. So make sure you follow the link down below.